Hi, everyone. Okay, so I believe this example was left over last week, right? So first, for today, we're going to do this example. Okay, let me see what I did. Okay, so this is a very unrealistic elevator example. Because in this example, an elevator, you can pick up one. This example, an elevator operates in a 4-story building according to the buttons push it inside the elevator. Okay, there is a person on the outside cannot call the elevator, which is very unrealistic, right? In the real world. So consequently, I would say the only way to get the elevator is for somebody else to get off at your floor. Okay. And we assume that the passengers who enter the building at the first floor wish to use the elevator, and half go to the second floor, and the other half divides equally between the third and the fourth floor. And we also assume that the passengers above the first floor wants to go to the first floor in 80% of cases. Otherwise, they are equally likely to want to go to the other 2 floors. Okay, that is our assumption. Let me give you a couple of minutes. Why don't you think about how to define the state of the system so that you can construct one-step or one-stage transition probability matrix later. Okay? Close this door. So how did you define state of system? Because there are 4 different floors, right? First floor through 4th floor. How to define each state of system would be the, the location of the elevator, which will be either 1st floor or 2nd floor or 3rd floor or 4th floor at the end of each trips. Okay? So here, how to define state of system. I would be the location of the elevator. So obviously I can take 4 different values, 1, 2, 3, and 4, right? And in that case, stage n will be the trip number of trips. Okay. So keep in mind that this self-service elevator operates only depends upon the buttons. Push it inside the elevator. Okay, which is very unrealistic. So using this state of system, let's construct one-step transition probability matrix. Okay? So let me use smart board. Okay. Okay, so let me draw this way. So we have 4 different flows, right? Let's say 4, 3, 2, and 1, right? So let's start from first flow. And let's see what transitions can occur starting from the first flow and the corresponding transition probabilities. Okay? So what transition can occur? So do we have this transition 1 to 2? Right? What is this? 50%, right? So it's going to be 0.5. Do you have this transition 1 to 3?
Divided by.
How much is that? 25%, right? So it's going to be 0.25. And then the other 25% will go to the first flow, right? So we have 0.25. Is that right? How about this probability? 1 to 1 is 0, right? Oh, thank you. So I can finish the first row of the P matrix, which is 1 to 1 is 0, right? 1 to 2 is 0.5. 1 to 3 is 0.25. Okay, let me delete this part. And then 1 to 4 is 0.25, right? Now let's start from state number 2. Again, we were going to have same state, right? So now we start from state number 2. What transitions do we have? 2 to 1 is 80%, 0.8, right? How about 2 to 3? Is only 10%, right? 0.1, and then 2 to 4 would be 0.1, right? So we have 2 to 1 is 0.8, 2 to 2 is 0, 2 to 3 is 0.1, 2 to 4 is 0.1, right? So similarly, we can do starting from state number 3 and 4. 4, 3, 2, 1. And 4, 3, 2, 1. So we can start from state number 3. Then it's going to be very similar to what happened starting from state number 2, right? So 3 to 1 is going to be 80%, right? 3 to 2 is just 10%. 3 to 4 is 10%, right? Of course, 4 to 1 is again 80%, right? 4 to 3 is just 10%. 4 to 2 is 10%, right? Easy, right? So let's complete our one-step transition probability matrix. It's going to be 0.80, is 0.1, right? And then 0, 0.1, 0.8, and then 0.1, 0.1, and then 0. Is that correct? Right? Of course, eventually you need to combine all of these transition diagram, right? So it will be somehow complicated because your transition diagram should include all of these transitions, right? It's going to be 1 to 2, 1 to 3, 1 to 4, right? And then 2 to 1, 2 to 3, 2 to 4, and even starting from 3 to 1, 3 to 2, 3 to 4, and then 4 to 1, 4 to 2, 4 to 3. So it's pretty complicated, right? But that's what you're supposed to do because those are identical, right? From this P matrix, you should be able to draw this transition diagram or vice versa. From this transition diagram, you should be able to obtain this P matrix. Okay? Any questions so far? Okay, so if we go back to the so if we go back to the problem description, then we need to address the probability that you will find the elevator when you enter the building on the first floor. Okay? So what do we need to have? What would be the answer for this? How about pi 1? Okay. What is pi? That is the steady state probability or limiting probability, right? What does it mean by that? After a long period of time, the state of system becomes stable, and then for example, I don't know how much value we're going to have. For example, if pi 1 is just 0.05, 0.05, just for example, so it's just 5%. If you assume that pi 1 is just 5%, then what does it mean? When you get into this building on the first floor, there is only 5% of chance that the elevator is in there, right? So you are able to get in. Does that make sense? So this is not the correct value. We're going to compute pi 1 because you are supposed to get pi 1 to answer this question. Okay? So how do you get pi 1? We need to use pi equals pi p in matrix form, and then sum over pi I should be equal to 1. We're going to use this formula, right? That's what we've done a couple of times. So pi 1 should be pi times the first column of this P matrix. So that's going to be 0.8 times pi 2, pi 3, pi 4, right? Likewise, pi 2 equals pi times the second column of this P matrix. So it's 0.5 pi 1 plus 0.1 pi 3 and pi 4. And then pi 3 should be pi times the third column of this P matrix, which is 0.25 pi 1, 0.1 pi 2 and pi 4, right? And pi 4 is pi times the last column of this P matrix. This is 0.25 pi 1, 0.1 pi 2, pi 3. And you remember the system of linear equations are linearly dependent. So what you need is take out one of these four equations. Just arbitrarily choose one. So for example, you can choose this and then take it out. And then add summation of pi values equal to 1. Okay? So using these four equations, you should be able to get the pi values. Okay, any questions? And now go back to our slide. Okay, these are some important notations for the analysis of discrete time Markov chain. So we've already talked about the first three, right? One-step transition probability matrix and n-step transition probability matrix, probabilities, and then steady-state probability or limiting probabilities, right? Those are pi's. Now, we are going to talk about these three today, okay? Just one by one. Okay, first, n sub ij, which is the first passage time, okay? That is capital N sub ij. In other words, that is the number of stages at which the system first reaches, which means first hit certain state j, starting from state I. Okay? That is what is called first passage time. What about the next one?
Like in the previous example, it was the education,
right? I'm going to show you with an example later. Okay, next is about the first passage probability or first visit probability, some people say. Okay? It is represented by F instead of P. Okay? So there is the probability that the system will first reach state J in exactly n steps. Of course, starting from state I. Okay? And recall that the P sub ij is the probability that you start from state I and the system will be in state J after n steps. Okay? So in this case, P sub ij to the nth power? Perhaps. It's not going to be the first visit. Okay? So it does say after n steps, the system will be in state J. But that may not be the very first visit. Okay? That's the main differences between P and F. Okay? Here the keyword is the first. Okay? And now I'm going to show you how you come up with this equation. Well, first, let's take an example. Okay, I just want to give you the basic concept, how you can distinguish this F from this P. Okay, those two probabilities. So first of all, let's take an example. So let's take an weather forecasting example that we talked about probably last week, right? So in this example, we wanted to know the probability that the weather is cool on Friday, given the weather is hot on Wednesday. And because starting from Wednesday, Thursday, Friday is the 2-day weather forecast, right? So the 2-day weather forecast was found in this P square matrix, right? That is because the desired probability can be computed by conditioning on Thursday's weather. So this is the desired probability, right? P sub 1,3 to the second power matrix. So there is the probability that the Friday weather will be cool, given the Wednesday's weather is hot. Consists of these 3 different cases, right? Because there are 3 different weathers on Thursday, right? And, in general, all of this information of 2-day weather forecast can be obtained from the P-square matrix, this. Because this P-square matrix is 2-stage transition probability matrix. And in this example, of course, we assume that each state, each transition takes 1 day, which means 1 stage means 1 day, okay? And because there are 2 days gap between the Wednesday and Friday, the desired probability, this probability can be obtained from 2-stage transition probability matrix. That's what we discussed last time, right? So we know that. What is P sub 1,3 to the second power? Okay, what is this? Now, what is this then? You remember this matrix? This probability, first visit probability, state that starting from state I, the system will first reach state J in exactly n steps. So, in word, that's going to be the probability, this should be the probability that Friday's weather will be cool. And that's going to be the very first time. Okay? Given the Wednesday weather is hot. Okay? Again, the key word here is the first time, because we are talking about first passage probability. Okay? First visit probability. So what is the major difference here? We need to take this out, the last portion, right? Why is that? Because in this case, Thursday's weather is already cool, right? Although the Friday's weather is cool at the moment, this is not the very first time happened, right? Because the cool weather has already happened previously. Is that right? Starting from Wednesday. So, in order for you to get this probability, you need to take this out. Does that make sense? Okay? So keep in mind this. These are the major difference between these two probabilities. Okay? Regular transition probability, P, and then this is the first passage or first visit probabilities. Okay? Any questions? Okay, and the n-step first passage probability or n-step first visit probability can be computed like this. First, n-step transition probability, which is P sub ij to the nth power, can be computed by conditioning on the step k at which the system first reaches state j. Actually, we can visualize this equation. So I can show you this. Okay, let me close this out. So consider this. Let's say this is the timeline, okay? So we have starting from 0, 1, 2, and so on. And we have k minus 1, k, and k plus 1. And then keep going. Eventually we have m minus 1, and m plus 1, m plus 2, and so on. Okay? So let's say starting from state I here. Okay? So right now you are in state I. Okay? And then after, let's say, k steps, the system first hit state J, okay? So this is the very first time you hit state J after k steps. Then what is this probability? This probability is f sub ij to the kth power. Is that right? Because it starts from state I, and after n step, the system first hit state J. So by definition, this is this. Is that right? Okay. Now, starting from here, and then after n minus k steps, okay? So where do we go? Starting from here, after n minus k steps, so we land right here, all right? And then let's say the system is in state J, okay? And what is this? starting from state K, after n minus K steps, you are still in state J, okay, from J to J, after n minus K steps. What is this? That's going to be P sub JJ, right? And then n minus K power. Does that make sense? Is that right? And then let's think in this way. What is this? Starting from state I, right here, after n steps, which is, again, right here, the system is in state J. What is this? That's going to be P sub ij to the nth power. Does that make sense? Is that right? So I can say that P sub ij to the nth power is exactly same as sum over k equals 1 to n. And then P sub, this one, P sub P sub jj n minus k times this, f sub ij and kth power. Okay? That's why we come up with this formula, okay, which is exactly same as this, okay, this part. Does that make sense? Okay? Okay. And for the computation of these first passage probabilities, we're going to solve for what is that? N-step first passage probability. Okay. And so what I did from here to here is just take out the nth term. Okay. So that's why I take out the nth term here, and these are left over. See, originally k was from 1 to n. Now is 1 to n minus 1, because I took out the nth term. Okay? And you know, okay, I'm going to take this. You know, any number except 0 with the exponent 0 becomes 1, right? And then if we move this to the left-hand side, then we will end up with this formula. Does that make sense? Right? So from here to here, I just move this part to the left-hand side. And of course, no, actually, I move this part, right? I move this part to the left-hand side. Then we end up with this formula. So to obtain the first passage probability, we need to do what is called recursive computation. Okay? So in order for you to get this first passage probability, these are what you need to do step by step. Okay? First, you're going to compute the power of P, which is this. And then, by setting this, because this is always true. Okay? We were going to compute this, and then knowing this and this, we're going to compute this. And then we're going to move on. Okay? That's what you are going to do right now. Okay? So I'm going to take the same example. So we're going to revisit the self-service elevator problem that we just discussed earlier today. And right now, okay, this is the edit part. So we want to know if the elevator is not at the first floor, but at the second floor, how many trips is it expected to make before returning to the first floor? And we're going to answer this question later today. Okay? Okay, so this is what we've already done, right? We defined 4 different states, and then using this state, we constructed one-step transition probability matrix. And this is the transition diagram, okay? Okay, now here, I provide the 1, 2, 3, and 4 steps transition probability matrices. Now, using this, all of this information, let's compute the first passage probabilities, okay, which is f sub to 1. Okay, specifically, we're gonna go with f sub to 1 to nth power. Okay. So we're going to use the recursive computation that I've mentioned earlier. Okay? Okay, I think I should use the smart pad again. What's that? Okay, so first, if n is equal to 1, then we know that f to 1 is equal to p sub to 1, right? That is always true. So what is this value? That's going to be 0.8 here. Right? So that's going to be 0.8. All right? Now, if n equals 2, what do you have? You're going to have f to 1, 2, right? Minus what? We're going to use the same formula. K equals 1, 2, 1, actually, right? And then P sub 1, 1, 2 minus K times F to 1 K. Are you following me, right? So I just use this formula, right? So we're going to keep coming back to this formula. So what is this? What did I do wrong? Something is not right. Oh, I forgot one of them. Okay, so let me rewrite this. If n equals 2, then actually this part should be p, right? And we're going to have f21, 2. Is that right? Sorry about that. Okay. Now, did I miss anything? Is that right? Let me just double check before I go further. Otherwise, we might need to come back again. Okay, so looks like this is correct. Okay, now this is same. And what is this part? So k can take only one value, which is 1. So we're going to have k equals 1, k equals 1 down here, right? So we're going to have p sub 1, 1, 1, f sub 2, 1, 1. Okay? And we know all of these values from the given matrix, right? Probability matrices. So what is this? Is that going to be 0.16, right? From this matrix, right? 2, 1 is right here. So the first value is 0.16, and then what is the next value? It's going to be 0, and f21, what is that? That's going to be same as this, right? 0.8. So we have here 0.16 minus 0 times 0.8. Is that right? So this part is 0. So we have 0.16. Is that right? So let's keep going. If n equals 3, then what do we have? It's going to be f21, 3 equals p21, 3 minus sum over k equals 1 to 2 p sub 1, 1, 3 minus k, is that right? Times f21 to the power k. Is that right? So this is exactly same as p sub 21 to third power minus, now at the moment k takes two different values. It's 1 and 2, right? So it's got to be p sub 1, 1 square f sub 2, 1, 1 minus p sub 1, 1, 1 f sub 2, 1, 2. Is that right? So let's get all of these value from the given probability matrix. So this is going to be 0.672, right? Minus, what is this value? It's 0.8 what is F21? F21 is 0.8, right? From up here, right? And then, what is this? Again, this is going to be 0. And then, what is this? It's from up here, right? Which is 0.16. So we have 0.16. And from my previous computation, this is 0.032. Okay? So let's do this one more time. If n is equal to 4, then we're going to have f sub 21 to 4th power equals p sub 21 to 4th power minus sum over k equal to 1, 2, 3. And p sub 11, 4 minus k, f sub 21 to kth power. Okay? So it's getting complicated, right? More and more complicated. So this is going to be like this. This time k takes 3 different values, 1 through 3, right? So if k equals 1, then this is going to be 3, f21, 1. If k equals 2, then this is going to be 2, f21, 2. If k equals 3, then p11, 1, f21, 3. Is that right? And then this is going to be 0.2624, right? And because this is 0, right? So this is 0 minus 0.8 times 0.16 minus 0.16 times 0.8. Hold on a second, am I doing wrong? This is going to be 0.032, right? So I got to double check this, but previously I have 0.0064, but I want you to double check all of this value, okay? It's going to be easy to do. So anyway, eventually,
again, from the beginning, how we n equal what?
What?
N equal what?
What do you mean? This one?
Yeah. How we?
Why this is true?
Yeah.
Because this is always true. This is one-step transition probability, right?
Okay.
This is also like a one-step transition probability. Because we consider only one step, right? Because
And it's previously.
yeah, this is just like, think about the weather forecast example. Today is hot, and tomorrow is hot. What is the probability? That's going to be p sub, for example, 1, 1 to the power 1, right? And then that is exactly the same as f11. What is this meaning? After one step, you're going to first visit, I'm sorry, it's not a good example maybe. Let's say you start from moderate weather today, and tomorrow is going to be hot, okay? Then the desired probability is p sub 21 to power 1, which is exactly the same as f sub 21 to power 1. Because by definition, this probability saying that starting from today's weather, which is moderate, tomorrow you're going to be hot, And that's going to be the very first time happen. Is that right? So if you consider one-step probability matrix, then this is always same. F sub ij to 1 is always same as P sub ij to 1. Because we just consider one-step transition probability, one day forecast, 1 year forecast. Okay? If you consider maybe second power or third power, which is greater than 1, then sometimes this can be same, but highly likely it's not going to be same. Because of this case, right? For example. Okay, so where was I? Okay, so in summary, what I have is this is the n values 1, 2, 3, 4. And then we have computed f sub to 1 to nth power. And then this was 0.8, right, from the top. And then next value is 0.16. And then what is the next value? 0.032. And then we just got 0.00064. So you just need to keep going this, okay? So this is how you can compute first passage probability. Okay, this is very tedious job. Yeah, I have to say so. Okay. But if you are good at computer programming, this wouldn't be any problem at all. Okay, you just need to make a programming code, then let the computer run. Then you're going to get a whole lot of different values. Okay. Okay, now let's talk about mean first passage time. So the mean first passage time is represented by m sub ij. And like it says, it is the expected number of stages at which system first reaches state j, starting from state I. Again, the keyword is first. Okay? So mathematically, there is the expected value of n. That is the first passage time, right? We talked about earlier today. So in the elevator example, we can compute this, right? Because we just computed these values, right? So what you need is just multiply n. Is that right? So let's go back to what he did. So I'm going to add one more column here. That's going to be n times f sub to 1 to n power. So what you need is just multiply these two values. Okay, 1 times 0.8, which is 0.8. 2 times 0.16, that is 0.32. 3 times 0.032, that is 0.096, right? And then 4 times this. What is this? 0.0256. Is that right? So you need to do this. Keep going. Then you're going to see that if you add up everything, then It's going to be very close to 1.25. Okay? And actually, there is another way for you to computing this infinite sum, okay, which is using this formula. Okay. So this is the formula that you can use instead. Okay. So this is how you need to do when you compute this, when you use this formula, okay, to get m sub ij. That's how you use that. Again, using the same example, I'm going to show you how to get this, okay, how to use this formula right now. Okay, what is this? So we are going to get the value of m sub 2, 1. By the way, what is this meaning, m sub 2, 1? By definition, this is the expected number of trips required to reach floor number 1. First floor, if the elevator is currently in the second floor. Okay? So what is that? That's exactly what you need to do to answer this question. Okay? So I gotta say the answer is m sub 2, 1. Okay? That's why I want to show you how to compute m sub 2, 1 using that formula. This formula, oh, what is that? This one. Okay? So let me write down the formula that you are going to use. That is ij equals 1 plus sum over k is not equal to j, p sub ik m sub kj. Okay, so we are going to use this formula. So to compute m sub ij, m sub 2, 1 in this case, from this equation requires that we also compute m sub 1, 1, m sub 3, 1, and m sub 4, 1. So in this case, m sub k1. Okay, that's how we are going to compute. In this case, k is not equal to what? 2. Because k is not equal to j. What is is that right? No, k should not equal to 1, right? Because here k is not equal to j, so k is not equal to 1. Is that right? Okay. So let's do that. What if I is equal to 1? What do we have from this formula? Then we are going to have m 1, 1. Okay? First. And it's going to be 1 plus p sub 1, 2, right? M sub 2, 1. And then P sub 1, 3, M sub 3, 1, and P sub 1, 4, M sub 4, 1. Is that right? What if I is equal to 2? It's going to be M sub 2, 1, right? So we have 1 plus P sub 2, 2, M sub 10, P sub 2, 3, M sub 3, 1, P sub 2, 4, M sub 4, 1. So if you keep going, if I equals 3, then that's going to be M sub 3, 1, right? 1 plus P sub 3, 2, M sub 2, 1, right? P sub 3, 3, M sub 3, 1, and P sub 3, 4, M sub 4, 1. And finally, if I equals 4, then what do we have? M sub 4, 1 equals 1 plus P sub 4, 2, M sub 2, 1, P sub 4, 3, M sub, 3, 1, and P sub 4, 4, M sub 4, 1. Okay. Here we know all of these p-values, right? All of these p-values are known. And all of m's are unknown variables. Is that right? So if you use the real value for those p's, then what do you have? So instead of p12, I'm going to have what do you have is 0.5, right? And instead of P13, we have 0.25, right? Instead of P14, we have 0.25. And instead of P22, we have that 0, right? And P3 should be 0.1, right? And then P24 is also 0.1. Is that right? Are you following me? Okay, and this part, P32 is what? It's 0.1, right? And P33 is at 0, right? And then P34 is 0.1. So if we keep going, this is going to be 0.1, and then this is 0.1, and finally, what is P44? That is 0, right? So we have this. Since we have 4 unknown variables, m sub 1, 1, m sub 2, 1, m sub 3, 1, m sub 4, 1, and we have 1, 2, 3, 4 different equations. So you should be able to get m values by solving this linear system of equations. Okay? And you can manually compute them, but last time I mentioned probably if you go with Gauss-Jordan method, it will be easier So I got piece M sub 11 is 2.25. M sub 21 is 1.25, which is same as M sub 31 and M sub 41. Okay, but please double check this. Okay, make sure you got the same values as mine. Okay, so anyway, going back to the our slide. The answer for the last question is M sub 21. Okay.
M21?
Yes. And one more thing. Okay, here, the bottom of the screen, I've included this. The mean recurrence time, which is represented by M sub ii. Sorry. So the starting point and ending point is same. Okay? So that's why it is called mean recurrence time. In other way, that is the expected number of steps, expected number of stages between visit to the same state I. Okay? That is going to be the reciprocal of the steady state probability of state I. This is very useful if you remember this. Okay? So which means if I view M sub I, then you should be able to get pi values using that, right? So I'm going to show you where, you can use this. Okay, probably next time I'm going to give you some exercise problems. Then we're going to deal with a series of questions, okay, which is related to all of these concepts we've learned so far. Okay, so these are all for today. And let me know if you have some questions related to what we've been talking about so far. Okay, feel free to email me or you can stop by my office. Okay, thank you very much. Bye-bye.